Alright, so the next one we're going to take a look at is one that has a potential energy versus displacement graph. Now, it's one that follows a shape kind of like this, where our zero position is at 0. And so our potential energy is actually going to equal 0 in the middle. We've been told that the mass of this object is 3.0 kilograms, and that it's being subjected to a restoring force. Here's actually a picture of the graph itself. I'll try and get something a bit better put up in the video online. I have trouble drawing it effectively to scale. And so what we're going to do is take a look at the questions. We're also told that it has a total energy of 0.4 joules. Okay, 0.4 joules comes up to about here on our graph. So here's 0.3, here's 0.2, 0.1. Okay, now, first question is, what's the object's potential energy when it reaches a displacement of 4 centimeters from the equilibrium position? Well, 4 centimeters happens about here. Let me get a different color so that we can see that, hopefully. So 4 centimeters is going to happen right at about here, which puts us pretty close to in between 0 and 0.1. So if we're at 4 centimeters, right here, our potential energy is about 0.05. That's what we see here on the graph. That's what it corresponds to. So our first part, A, our potential energy at 4 centimeters is equal to about 0.05 joules. Okay, that one's just reading the chart and seeing what energy, potential energy, corresponds with a given displacement. Okay, B, what's the farthest the object moves along the x-axis in the positive direction? Well, what's the most energy the object has? In this case, we were told that the maximum energy, the total energy that the system has, is 0.4 joules. So the highest it could actually go on this is 0.4 joules. When it gets up that high, it means all of its energy is in potential energy, and so it's got none left for kinetic energy to actually move, and so it's actually going to come back. This is what gives us our simple harmonic motion. It continues moving back and forth. The furthest it can get is based on its total energy. 0.4 joules, if I actually look on the graph where that corresponds, that should come up to about 10 centimeters. So for B, we end up with 10 centimeters is the farthest it gets. And that's the farthest it gets because all of its energy is in potential energy. No kinetic energy to move farther. And it ends up falling back in, down the graph, back towards the middle, and it's going to go back and forth, back and forth. In fact, because 0.4 joules is its total energy, it'll actually come out to here, which corresponds to, surprise, surprise, negative 10 centimeters. So our amplitude for our simple harmonic motion is 10 centimeters, because that's the furthest out it goes. Now, if I did something to this, maybe gave it a push and put more energy into the system, then I could get it up higher, maybe off the graph. Or, if I pushed it a little bit and slowed it down some, I could remove some energy from the system and maybe have it go back and forth. If I eliminated half of it, it would only go up to here. That sort of thing. Okay. Next one, C. Determine the object's kinetic energy when the displacement is negative 7 centimeters. Okay? Well, when I look on the graph, let me get yet another color. Negative 7 centimeters happens right at about here. Negative 7 cm. And that corresponds, when you read on the graph, to about 0.2 joules. Okay, well, at negative 7 centimeters, C, My potential energy at that point, -7, equals 0.2 joules. My total energy, which equals my potential, plus my kinetic, equals 0.4 joules. We haven't changed the total energy in the system. Okay, so plugging this in, I've got 0.2 joules plus my kinetic energy equals 0.4 joules. I subtract 0.2 from both sides, and I find that my kinetic energy is equal to 0.2 joules. And that is at -7 centimeters equals x, our position. Okay, that's reading the graph to find our potential energy value and then using that with our knowledge of the total energy in the system. Finally, the next one that we're going to look at least for the video here, is going to be part D. What is the object's speed at x equals 0? In other words, how fast is it going when it's going through the equilibrium position? D. Well, as we've mentioned before, when it's going through the equilibrium position, back over here at 0 cm, we have no potential energy. We actually have all of our energy in kinetic energy. So we know that our total energy equals our potential energy at 0, plus our kinetic energy at 0. Our potential energy was 0 joules. So that means 0.4 joules, our total energy, equals 0, plus our kinetic energy. And that means that 0.4 joules equals 1/2 mv squared. We know our mass, it was 3 kilograms, so I've got 0.4 equals 1/2 times 3 kilograms. Technically that's joules. V squared. If I solve this, V is going to be equal to 0.516 meters per second. In other words, about 52 centimeters per second. As to the original question that showed up on the homework, part E deals with the string being cut, this being a pendulum going back and forth, and right as it gets through the equilibrium position, when it's got this velocity, we cut the string and let it go flying, and we want to find out how far it goes if it falls 1/2 meter. Well, in that case, it just becomes a projectile motion problem. You can check the videos we have on those for projectile motion as a reminder on that. In this case, our initial velocity, it's all in the x direction, and it would be 0.516 meters per second. We assume that this is on Earth, and so you would use just the standard setup. We'd have no initial velocity in the y direction. So luckily, it avoids a quadratic, and it becomes a pretty easy solve. So this is a problem in which we use a potential energy graph.